Hi everybody. So this is our video that supports Trig Identities #1 booklet here, this guy. And this is really the last section of the entire course that we're talking about. There's a couple of Trig Identities booklets to get through. See how many we get through before the end of the year. But in many ways this is like math yoga, if I can put it that way. And it has to do with the idea of grand substitutions. So in this video we'll be talking about the overview and the kind of the theory behind these grand substitutions that we'll be doing. And we'll be looking at some of the main trig identities that you'll need to keep track of. And it's probably a good idea to write down your trig identities when you see them. I'll make notes to them as we move along because you're going to need to have them at your fingertips pretty much as we go through some of your work. And we'll be looking at some rather complicated type questions that if you don't know what's going on, it's going to look completely foreign to you. But there's several little tricks and keys, that we can use to unlock the doors to these questions that once you see them, then they fall apart quite easy. So you just have to know a couple and have these things. It's kind of like your times tables. You have to have them kind of memorized a little bit. Now, obviously trig identities aren't as crucial as your times tables, right? But in this work, having quick access to them makes your life a lot easier. So let's go through some of the original proofs and basic ideas. So one of the things I'm going to try to get you to do is to try to solve a question like this. And unless you know how to approach this, you're going to probably run into a brick wall. So do I cancel the sine first? Do I cancel the cosine first? Do I multiply cos to both sides? What am I doing? So what we're going to do is we're going to sub this out for a single expression. And this actually equals tangent. If you scroll back a little bit in the video, you'll see sine divided by cosine is equal to tangent. And I can rewrite this as tangent theta is equal to 2. But let's first of all understand why that is the case. And to do that, we have to go back to our polar coordinates. So remember x, y, and r and all that kind of stuff. So let's take a look at that first. So I'm sure you remember, hopefully you remember, our polar coordinate system, right? So, here's our point. We can label that as an x and a y value, or we can label it as an r and a theta value. So if I was to do the sine, right, the sine of this theta here, well, it's opposite over hypotenuse, right? Sine SOHCAHTOA, right? So opposite over hypotenuse, but because we fixed the angle, the opposite value is the y, and the hypotenuse is r, right? So sine is y over r. So I'm going to list cosine and tangent, and we'll have a look there. Okay, so here we have sine, y over r, cos, x over r, and tangent is y over x. And part of the job of this section of the unit is to deal with what we call a proof, or a formal proof. I'm asking you to prove that sine over cosine is equal to tangent. And the nature of a proof requires us to use things that we know are true before we can state that this is true. So we don't necessarily know this right now. I've told you that it is, but we haven't seen a proof for it. So we've come to understand or know that sine, cosine, and tangent are defined like this. And because these are defined like this, we can use these bits of information to help us prove this to be so. But we cannot say that this is so until we have proven it. So, let's have a look at how the proof is structured, because you'll be doing a few of these. Okay, so going back to first principles, right? Sine theta up here is defined as y over r, and cos theta is defined as x over r. So, because we have that up here, right, that comes from our things that I just mentioned. So, I have y over r divided by x over r. And let's see what happens when I work through the division on that. Some of you who are really good at dividing fractions can already see how this plays out, but let's just go a little slower. Alright, so I write it out as y over r divided by x over r. And remember, when you divide fractions, you have to flip the other side of the fraction. So let's do that. Okay, so y over r divided by r over x, not divided by, sorry, times, because you flip it and you change it to a times. Right, so times. And now you can easily see what happens to the r values here, right? The r value here and the r value there, they cancel out. So let's do that. Let's cancel those guys out, and I'm left with y over x. Y over x. And that is what I have over there. So for any value of theta, and you can do this on your calculator if you like, you can go sine of 20 degrees divided by the cosine of 20 degrees and get a decimal for it. If you like, you can try it, and then go the tangent of 20 degrees, and those will be the same values all the time, right? It's you know, it's a fact that we can use and exploit. We've proven this to be so because whenever you divide sine by cosine, you're left with y over x, which is exactly what tangent is. So we've just made a proof, right? So I've got a couple other proofs that I want to discuss with you and show you. Okay, so here's another example, all right? Cosine divided by sine, right? So let's go through the proof of that. It's the same as the proof that we just did, but we have to, you know, it's slightly different, but it's the same style. So let's go through that. Okay, so x over r divided by y over r, so x over r times the reciprocal, right, because that's dividing fractions, remember how that works. And so again, the r values cancel, and I'm left with x over y. Okay, and x over y is cotangent. Boom, boom, boom. Okay. Right, there we go. Right, so now we have both sides of my proof ledger equal to each other. And when we have that, we can say this. This is just Mr. Gerard's crazy ways. Well, not really. But we can say BSE. What's that? Both sides equal. And that's part of what you're doing today. Is part of what you're doing for the rest of this unit is to make these proofs happen. So both sides equal, right? And because it's awesome and it's really good when you do that, I put a little money symbol because it's money in the bank. Okay, you don't have to do that, but anyways, our job is to create a situation where we have both sides equal. So when you have an expression on this side over here equal to an expression on that side over there, you've fulfilled the obligation, the burden of proof, right? You've made both sides equal to the same expression, and that allows us to then use these proofs in other ways. So let's build from there. So these proofs that I have here, right, these are what we call our primary identities. They are the truths that we can establish from the system of polar coordinates that we've created and learned so far. So they're kind of like our first building blocks. And out of these building blocks, we can make bigger building blocks, kind of like atoms and molecules. These are like your atoms, and now we're going to start making molecules, which we already kind of did. Those last two the last two proof charts that we had, those were what we would call our secondary identities, right? Things that have been proven using our primary identities. And there's three more major proofs to your secondary identities. They're called Pythagorean proofs, so let's start there. Okay, so this guy here is called, it's one of our secondary identities. We have yet to prove it, so we can't say that it's true yet. It is, we'll prove it to be so, but we can't say so until we prove it. So this is our proof of how we do this. And we use the same tricks. We go up here, we find sine, we find cosine, and we see if we can do a couple shenanigans to make this work. So let's have a look. Okay, so sine is y over r, so y over r squared, and cosine is x over r, so x over r squared. And now we got to find a way to make that equal to 1. Okay, well, this is where people usually kind of get lost unless they have a guide. So let me guide you through this, because the next two are similar, and you'll probably be able to do the other two in the same way. So let's check this out. So I can take the, the squared off of the bracket, right, and put the squared on both terms, right? So y over r squared is like y squared over r squared. Scroll back in the video if you need to, see how that plays out. So we have that situation there. Okay, now notice we have a common denominator, right? R squared is common, so we can join those two fractions. Okay, so I can write it like that. Y squared plus x squared divided by r squared. So how does that equal 1? So, Pythagoras. Pythagoras is the man. If you ever take the opportunity to study Greek philosophy, make sure you take a stop at Pythagoras, because you want something to blow your mind with a lot of cool ideas. Pythagoras has got a lot of cool ideas. He was a vegetarian, for one thing, and he believed in karma and reincarnation. This is long before Jesus Christ and all that sort of stuff. So it's like 400 years before. So he's got a lot of kind of excellent philosophical ideas. But Pythagoras Theorem, right, a squared plus b squared equals c squared, applies here. It's just we don't use a, b, and c. We use x, y, and r. Let me write that out and show you. All right, Pythagoras Theorem, in the context of our polar coordinate system, looks like that. X squared plus y squared equals r squared. Well, x squared plus y squared, that's just backwards, but when you're plussing backwards, it doesn't matter. So this is r squared, because x squared plus y squared is r squared. Right? We have that up here. So r squared over r squared is equal to 1. And now I have both sides equal. Yeah. So this is what we call our first Pythagorean identity. And there's two others. So we'll look at the proofs for those. Okay, so the next one is tangent squared theta plus 1 is equal to secant squared theta. And for any theta, you can put any theta in there, plug that in, calculate it out on this side, and you get the same thing over there. You get the same value on the other side. So let's have a look at the proof. I'll set it up for you. It's kind of the same situation as the last one. So maybe you want to try proving it on your own, or you could just wait a couple seconds and see what the video says. Okay, so I did a little cheeky shenanigan. So tangent, right? So tangent is y over x. And 1, I write as x over x. You're like, why would you do that? Well, I do that because it creates a common denominator. Okay, so let's take the squareds and put them on each part. And because we have a common denominator, well, you'll see. Okay, so I just took the squared and I wrote it on the y and the x. So, sorry, I'm missing a squared down here, but there we go. Okay, so I have a common denominator, so I can write it as a single denominator, and then I get y plus x squared. But we know what y plus x squared is, right? Y plus x squared is Pythagoras up here. That's why they call it Pythagorean, because we use Pythagoras, by the way, just saying. So that's really r squared on top. And what's r over x? So r squared over x squared is going to be secant squared. Let's take a look. There we go. R squared over x squared on this side from all this fancy shenanigans that we just talked about. And then r squared over x squared, because that's what secant squared looks like. That's what this little squared means, right? It means this. Right, we write the squared in between the secant and the theta, or in the tangent and the theta, or whatever, and the theta, to show this idea. And if we didn't put the brackets on it, then we would have like secant theta squared, and we would square the theta and then take the secant, so that would cause like massive problems. We don't want to do that. But in writing out all these extra brackets, it's just more work to do, so we just simplify the notation, right? Secant squared theta, so we're just talking, times by itself. Same thing over here, tangent and all that sort of stuff. So here's the proof of this Pythagorean identity. Now we've done two of them, so let's do one more. Alright, so the last one is this one. Now I erased the other stuff because now you can start to see why it's important to have those identities close at hand. Because you're like, oh, what's cotangent again? You have to think about it. And what's cosecant again? So if you have them written down on a separate sheet of paper, and I'll do this for you right after I've done all this. Okay, once if you have them written down on a separate sheet of paper, it makes your life a lot easier. So let's just go through this proof, and then I'll write out all this, the summary of those identities for us. Alright, so here's the proof. Cotangent we define as x over y. You can scroll back and check that if you like. 1 I'm going to write as y over y because that gives us a common denominator. And then I write this like that. I got Pythagoras Theorem on the top, so that's r squared. R squared over y squared, well that's what the definition of cosecant is. R squared over y squared. Don't believe me? Scroll back a little bit. Okay, so there's our last secondary proof, our Pythagorean proof. So let me summarize this for us. So our Pythagorean ones are here. Sine squared plus cos squared equals 1. Cotangent, all these guys that we just worked out in our t-charts are there. Plus we have tangent, sine over cos. We did a proof chart for that. Cotangent, the reciprocal, right? So the reciprocal of tangent, so flip the fractions, there's that one. And these three constitute our secondary identities. But from these, we can make many more, an infinite set of possible combinations more. So what I've done in the booklet is I've looked at a quick way to help you remember tangent, sine, and cosine. And I'm going to write these up for you as algebra triangles. So if you're stuck or whatever, you might want to just scroll to the, remember to scroll to the very end of this video to give you those values. And you can write, or I would recommend that you write them down on your sheet of paper for you. Okay, so I'm going to hold this up to the screen and I'll keep it there for a moment. And you guys should probably try to copy down these 6 t-charts on algebra triangles on a separate sheet of paper. So stop the video and copy these down because it's majorly helpful to do that, to have these at your fingertips. So yeah. If you think about an algebra triangle, now I know you guys have seen algebra triangles before, but check out this very first one, right? If I want to find tangent, I put my finger over tangent and I get sine over cos. Well, that's exactly what I have here. Tangent is sine over cos. Or cotangent, right, is cos over sine. So I'll explain how I got these algebra triangles next lesson, right? How we did that, and then what we can do with them, right? We'll start our very long and awesome, cool path of math yoga that we've got coming up. So I'll sign off on this video. And there's not a lot in this video that pertains directly to the booklet, except maybe these algebra triangles. But we'll be building upon these algebra triangles and doing some algebra in the next video. Okay, take care guys. Stay safe.